If you could take your seats, please. We're going to get started with the last session of the first day. And the title of this session is Engineering and Cryptography 1. So our first talk is actually pre-recorded. This talk is by Oded Naor, Mathieu Baudet. The talk is by Oded Naor. The paper's by Oded, Mathieu Baudet, Dahlia, Malkhi, and Alexander Spiegelman. And it's about a system called Cogsworth, Byzantine view synchronization. So what we're going to do is we're going to play a talk for you, and then Oded is going to join us live, and we are going to do Q&A. So let's get started.
Hi, everyone. My name is Oded Naor, and today I'll present Cogsworth, which is Byzantine view synchronization. I'm from the Technion, and most of this research was done during a research internship at Calibra. This paper is a collaboration with myself, Dahlia, Malkhi, Mathieu Baudet from Calibra, and Alexander Spiegelman from VMware Research. Now, just to get the most important thing out first, the name of the paper, Cogsworth. So Cogsworth is actually the enchanted clock from Disney's classic, Beauty and the Beast. And we wanted something, an illustrated character from a movie that represented a clock. I think it was shot on. By the way, there is a play of Beauty and the Beast. This is what Cogsworth would look like if he was real. So let's talk a little bit about the background and the model. So, like I said, this work stemmed from the Libra blockchain at Calibra. And we're talking about a permission blockchain. A permission blockchain has a predefined set of nodes, in this case n, and up to f, or a third of them, can be Byzantine. A Byzantine node may act arbitrarily, may just stop and fail, not send messages, act adversarially, collaborate with other Byzantine nodes, and so on and so forth. What's important is to say that this upper bound of a third is because that's what it is known to be the upper bound on the number of Byzantine nodes and still being able to solve classic deterministic consensus. Now, consensus means to reach an agreement on some input from one of the honest nodes. So if we look at it in terms of a blockchain, meaning running a consensus algorithm means to agree on one block, on one input. State machine replication, or SMR, is simply a multiple shots of one-time consensus. So means to run consensus algorithm over and over again. Again, in terms of a blockchain, simply means to agree on the entire history of the blockchain. Now, the model we work here is what we call partial synchrony model. In this model, time is divided into two periods. First, a period of asynchrony or unbounded message delivery, meaning a message sent will eventually be delivered, but without an upper bound. Then, an event in which we call GST, or global stabilization time, and after which, a time for a period of synchrony, where messages sent will arrive with some upper bound, denoted here as delta. Now, Nakamoto consensus has been proven to be secure in the synchronous model, meaning that when the entire execution is synchronous. Classic deterministic consensus can also be solved in a partial synchrony model. Now, most consensus protocols are divided into views or rounds. A node is always in some round. A round is simply a number, 1, 2, 3, 4. And in LibraBFT, as in other consensus protocols, nodes advance to the next view when they hear from two f+1 nodes. Again, f is the number of Byzantine nodes in the system. Now, progress in the protocol, progress means to add more blocks to the blockchain, is guaranteed when two f+1 honest nodes are in the same view and cooperate among them. So let's look at an example. This is an axis of the views and numbers. So it starts from view 4, 5, and so on. And let's say that this is the current state of the blockchain. So we have two f+1 nodes in view 4. They run the consensus protocol, agree on some input on a new block, and add it on the blockchain. Move to view 5, again run the consensus protocol, add a new block to the blockchain, and move to view 6. Now, in this example, what might go wrong from this time on is that from these two F+1 nodes which run the consensus protocol and are now at view 6, actually F might be Byzantine. And the Byzantine node may decide to cooperate and then stop. So let's look at an alternate run. Again, this is the state of the blockchain, and we have two F+1 nodes in view 4. F+1 are honest, and F are Byzantine. As in before, they run the consensus protocol, add a new block, move to view 5, run the consensus protocol, and move to view 6. But in view 6, the F Byzantine nodes stop, drink a margarita, and stop cooperating. So now what we have is F+1 honest nodes in view 6, and F other honest nodes in some view which is behind. View synchronization, the intuition behind view synchronization, is how do we get those F honest nodes which are behind to the same view as the F+1 nodes which are in view 6. So again, let's look at the timeline. Now the axis is time. And let's see three nodes, nodes 1, 2, and 3, which are honest. There is also a Byzantine node, which is not illustrated here. So let's say nodes 1 and 2 are cooperating with the Byzantine node, and these are the times where each node entered each view. So you can see that nodes 1 and 2 entered view 5, 6, and 7. And node 3, in this example, stayed at view 2 for some reason. But there was progress made because of the Byzantine node, which cooperated with nodes 1 and 2. Now the Byzantine node stops cooperating, and this is where view synchronization needs to come into play. We need some mechanism to bring node 3 to the same view as nodes 1 and 2. This will ensure us that progress will be made in the consensus protocol, more blocks will be added to the blockchain, and eventually they'll enter view 8. The time, the overlap between all the correct nodes executing the same round is when we say a view is synchronized. And this is the intuition behind view synchronization. We delegate this view synchronization to a task, a local task called a synchronizer, which we envision as a black box that has a single output and input. The output is proposed UV, so when your synchronizer tells you or signals you propose UV, you immediately start executing view V. It also has an input which we call wish to advance. This is used to tell your synchronizer that you want to move to the next view in the consensus protocol. So it can be for a variety of reasons, but this is used to signal when you're in view 7 and you want to move, for example, to view 8. Now, a synchronizer needs to achieve two properties, and these are eventual view synchronization, meaning just what I said. Eventually, we want all the honest nodes to execute the same view for a sufficiently long time, and we want this to happen for an infinite number of views. So again, in the example here, view 7, this green box where all the nodes execute view 7 for the same time, is a synchronized view. And we want this to happen for a sufficiently long time, meaning some threshold, predefined threshold. And we want this view 7 to happen an infinite number of times during an infinite run. The second property is named validity, meaning that nodes advance to a view only if an honest node wishes to advance to it. So a synchronizer will not signal to any honest node in the system view 8 unless there exists some honest node in view 7 which called wish to advance. This is what we call validity, and a synchronizer, in order to fulfill our specification, has to achieve or satisfies both properties. So let's recap what we did so far. So far, I've gave you the intuition and a semi-formally definition of view synchronization. It helps to simplify the abstraction needed for SMR. Usually in SMR consensus protocols, view synchronization is incorporated inside or encapsulated inside the consensus protocol itself. This view synchronization can be abstracted out and help to simplify SMR protocols. Next, I'll present three protocols or algorithms for view synchronization. The first two are view doubling and broadcast, are techniques or mechanism used for view synchronization that we extracted out from existing SMR protocols. The third is named Cogsworth, which is our own algorithm. I'll compare the three in terms of latency and message complexity. Now, the reason that we want to look at the latency and message complexity of the new synchronization algorithm is because there are SMR protocols such as Hotstuff, Casper, Tendermint, where view synchronization is the bottleneck of the overall performance. So if we can lower down the performance of view synchronization, we can actually improve the overall performance of those consensus protocols. LibraBFT is also one that can benefit from simplifying or achieving better performance in view synchronization algorithms. So the first protocol is a simple one. It's called view doubling. In view doubling, it's inspired from these works. In view doubling, all the nodes start view 0 with some initial duration beta. Now, there is no global clock. I haven't mentioned it, but there is no global clock that dictates when each node starts its local execution. Nodes can start their local execution at different times. In view doubling, every view is twice as long as the previous one. So view 0 is beta, view 1 is 2 beta, view 2 is 4 beta, and so on and so forth. And I think that you can imagine in your head that by doubling the time you spend in each view, from some point in time, all the honest nodes will spend at least a certain threshold in each view. And it works really well. The message complexity of this algorithm is 0. You don't need to send any message at all. You spend twice as long as you spend in the previous view, and you'll eventually arrive and you'll reach view synchronization. The problem is that latency is unbounded. I can always construct a run where it will be bigger than some predefined threshold until view synchronization is reached. The second protocol is broadcast-based. It's based on Bracha Reliable Byzantine Broadcast. It's a Byzantine broadcast protocol from the 80s. And the intuition is that you initiate a transition to the next view when f+1 nodes want to advance. Why f+1? Because from every f+1 nodes, at least one is correct or honest. So when you hear from f+1 nodes who want to advance, you also broadcast your intention to move to the next view. And you move to the next view when you hear from two f+1 nodes. Now I'll talk a little bit about the proof sketch. What I can guarantee is that, let's say this is the scenario, I can guarantee that when a node enters a new round, let's say node 1 enters view 5, I can guarantee that all the other correct nodes here, 2 and 3, will enter the same view within 2 delta after GST. Again, delta is the upper bound on message delivery. Now, the communication complexity is all-to-all communication, or quadratic. Each node sends each message per view to all the other nodes under random leader selection. I won't go into that. The latency, though, is constant. It will take 2 delta once the correct node enters a view for all the other correct nodes to enter the same view. So when we compare view doubling and broadcast-based, we can see that they're the opposite. View doubling unbounded latency and 0 message complexity, broadcast-based constant latency, but quadratic message complexity. Now the broadcast-based synchronizer ensures that every node receives a message by sending it to all the other nodes. What we want to do is optimistically decrease this communication cost. This is where Cogsworth comes into play. Cogsworth is a leader-based synchronizer. We start by allocating a leader to each view. So each view has one of the processes or nodes at its leader. When you send a message, instead of sending it to all the other nodes, you use the leader as a relay point, and I'll show you it through an example. Let's say that you want to send a message for view 5. We said that we allocate a leader for each round. Let's say Joffrey is the leader of view 5. To the leader of view 5. And then you wait. After GST, it should take a constant amount of time for Joffrey to gather all the messages from all the nodes. What I haven't said is that after you gather enough messages, the leader combines them into a threshold signature and simply sends one message, thus incurring a linear number of messages, not all to all, but all to the leader, leader to all, so it's linear. And then after GST, you should receive a response in a timely manner. So you wait. If you receive the response, great. If not, you move to the leader of the next view with the same message. Let's say that leader is thirsty, and you wait again. If you receive the answer from leader of view 6, great. If not, you continue to move until you reach an honest leader. An honest leader, after GST, will follow the protocol, send a message to all nodes, and everyone's happy. What you need to understand is that a Byzantine leader is not simply send all the messages, send a message to all the nodes or not. If you can, for example, send a message only to a subset of the correct processes. So you need to carefully plan the view synchronization algorithm for the case of a Byzantine leader. I won't go how we do it in here, but it requires careful planning. I will talk about, though, the latency and the message complexity of Cogsworth. So the latency depends on the number of consecutive Byzantine leaders until a correct leader is reached. So in our example, let's say you want to send a message for view 5. You have to go through 2 Byzantine leaders until you find the correct one. So you can see that it's a geometric distribution. You have the number of consecutive Byzantine leaders until a correct leader. The good thing about the geometric distribution is that the mean of this distribution is constant. Therefore, if leaders are allocated at random, latency is expected constant. Regarding message complexity, it's a bit trickier. And there is a difference between Byzantine and benign failure. A benign failure is a node that simply crashes and doesn't send messages. A Byzantine node can also act arbitrarily. In the Byzantine case, we get actually linear number of message complexity, optimal, linear. Optimal means that if the first leader of a round or a view is correct, you'll get linear message complexity. But in the expected case, we're still quadratic. In the benign case, we do better. We get expected linear communication costs. So let's recap and compare the 2 view synchronization algorithms. To the third one, you can see that Cogsworth, first, the latency is the same as broadcast-based. And also in message complexity, we do just as good as broadcast-based, and in certain cases, optimal Byzantine or benign expected, we actually get an order of magnitude better performance or message complexity than broadcast-based, which is the most used technique in current consensus protocols. Now, this is pretty good. What we would have liked to achieve would be to improve this performance or actually prove a lower bound on view synchronization message complexity to show that we reached the best milestone. So to summarize, we formally defined view synchronization here in this paper. We showed 3 view synchronization protocols, view doubling and broadcast-based, which we extracted from existing techniques used in SMR protocols. And now on Cogsworth, which is a new view synchronization algorithm, which in certain cases brings down the overall message complexity and can be used in SMR protocols such as Tendermint and Ostap and LibraBFT. We compare the latency and message complexity. And like I said, we achieve optimal linear message complexity and expected constant latency in the Byzantine case by using Cogsworth. What I will say is that we have a follow-up paper where we actually improved the performance of Cogsworth even better. So we took Cogsworth, we added more techniques, more methods, and we actually managed to get not optimal linear message complexity, but expected linear message complexity, even in the Byzantine case, which was pretty nice. This paper is already available on arXiv, and is currently in submission. So thank you very much, and I hope you enjoyed my talk. Thanks.
So I think that Oded will be joining us. Ah, there he is. Great. Oded, can you hear us?
I can hear you, yeah.
Great, we can hear you. If you would like to ask questions, please line up at these microphones. And while that is happening, I will ask the first question, Oded, if you don't mind.
Sure.
Could you perhaps tell us a little bit about the connection between view synchronization and consensus? Is it always necessary? Is it necessary in certain situations? What sort of role does it play?
So I don't want to say that it's always necessary. I'll say that most consensus protocols, especially deterministic ones, use view synchronization to some extent. Most consensus protocols are divided into views, and since you need all the correct nodes to be in the same view, basically most or all of them need some way to achieve this. View synchronization is simply abstracting it away from the consensus protocol.
And here?
Hi, Oded, it's Wasim. I've got a question for you. As you know, we were administering the peer review process for this paper, and one of the critiques that one of the reviewers had was that it seemed like the optimization that you put forward with Cogsworth was relying on multicast. So would you like to unpack your response to that?
So yeah, I think there is the review you're talking about mentioned that we use some special hardware to achieve the better performance, the better message complexity. And I think it was simply a matter of miscommunication, either in the paper or in the view process, but we're not using any special hardware or techniques to send a message. When a process sends a message to all the other nodes, it's simply end messages. So I think there was some confusion in the review.
All right, thanks.
I was kind of curious, is this the work you're doing applicable to coins that work on the, they're designed to like directed acyclic graph type coins, DAG coins?
So I don't know, it depends. I mean, it depends if those algorithms or coins need view synchronization. If they work in views and they need some way to get all the nodes in the system to execute the same view for sufficiently long, then yes. But I don't know the specifics of those protocols to give a better answer. Sorry.
Okay, great. Thank you so much, Oded.
Sure. Great.
Let's give him a round of thanks.